The research proposes a mini-batch method for solving nonlinear partial differential equations, PDEs, using Gaussian processes, GPs. This approach addresses the computational bottleneck of GP methods by applying a mini-batch algorithm. The method is based on stochastic proximal algorithms and reformulates the optimization problem to consider a small portion of samples at each iteration. This reformulation allows for the use of stochastic gradient descent, reducing the computational cost. The algorithm is designed to steadily reduce the error towards zero at a rate of 1, k plus 1, m, where k is the number of iterations and m is the batch size. The method's novelty lies in its ability to scale with the number of samples, making it more computationally efficient than traditional GP methods. The authors propose a mini-batch method for Gaussian process regression, aiming to approximate the solution of a GP problem with nonlinear observations. This method reformulates the optimization problem into a regularized optimal recovery problem, introducing slack variables and a regularization parameter. The mini-batch method iteratively updates the solution by solving a minimization problem involving the mini-batch objective function and a proximal term. The authors provide remarks on the method, including its extension to incorporate a preconditioned variant and how to compute the solution at a test point. They also discuss the importance of the Cholesky decomposition and the computational cost of the method. In the subsequent sections, the authors present the mini-batch method in detail, which reduces the computational cost to m cubed, due to solving smaller matrices. They establish a representer formula for the optimization problem, enabling efficient computation. A convergence analysis of the mini-batch method is provided, involving basic notions of convex analysis such as weakly convex and strongly convex functions, the proximal map, and Moreau envelope. The authors define stability for the optimization problem, showing that it is crucial for the convergence analysis. They also discuss implementation details, including the use of block diagonal matrices to reduce dimensions and the choice of the nugget parameter. The proposed method allows for smaller nuggets and more accurate results. Here is a combined summary of the 4 pages. The operator G pro xi psi, gamma is defined as the argument of psi, u, z, I, plus half of the squared norm of z minus z, where z is an element of x. This operator is said to be E-stable if the approximation of the expectation of psi using a mini-batch is bounded by E on expectation. A lemma is established, showing that if G pro xi psi, gamma is E-stable, the approximation of the expectation of psi using a mini-batch is also bounded by E on expectation. This stability property is crucial for the convergence analysis of algorithm 1, which is studied under the assumption of bounded linear operators and continuously differentiable functions phi. The weakly convexity of phi, I, is established, implying the convergence of algorithm 1. The authors propose a novel mini-batch method for Gaussian process regression, reducing computational complexity and memory requirements compared to traditional methods. The algorithm utilizes stochastic gradient descent with a mini-batch of data points sampled from the dataset. The authors prove that the sequence generated by the algorithm converges to a nearly stationary point as the number of iterations and batch size increase. Numerical experiments are conducted using Python with the JAX package for automatic differentiation, leveraging information between points in each mini-batch by taking nearby samples. The efficacy of the mini-batch method is demonstrated by solving a nonlinear elliptic equation and Berger's equation. Here is the combined summary. The authors propose a mini-batch method for Gaussian process regression, applied to nonlinear elliptic and Berger's equations. In the nonlinear elliptic equation, the true solution is prescribed as sin pi x1, sin pi x2, plus 4 sin 4 pi x1, sin 4 pi x2, for x equals x1, x2, element of omega. The Gaussian kernel with length scale parameter sigma equals 0.2 is chosen for regression. The algorithm uses n equals 1200 samples in the domain, with n omega equals 900 interior points, and stops after 40,000 iterations. The technique of eliminating variables at each iteration is employed, and the resulting nonlinear minimization problem is solved using the Gauss-Newton method. The mini-batch approach achieves accuracy comparable to that of the GP method using the entire samples, as shown in Figure 1. In the Burger's equation, the authors consider the nonlinear partial differential equation with nu equals 0.2 an unknown solution u. The anisotropic kernel is chosen with parameters sigma 1, sigma 2, equals 0.3, 0.05. The true solution is computed using the Kohl-Hopf transformation and numerical quadrature. The algorithm uses n equals 2400 points uniformly in the spacetime domain, with n omega equals 2000 interior points. Figure 2 presents the results of the mini-batch GP method with a batch size m equals 75. The paper introduces a rigorous convergence analysis of the mini-batch method, providing insights into the choice of batch sizes and their impact on convergence rates and solution accuracy. The authors observe that increasing batch sizes result in faster convergence rates and smaller losses, as demonstrated in Figure 3. The choice of mini-batch sample points significantly influences the performance, suggesting future work on investigating different sampling techniques. The paper also includes a detailed proof of key lemmas, such as lemma 2.5 and lemma 3.6, which are crucial for establishing the convergence properties of the mini-batch method. These proofs involve showing that the objective function is Lipschitz in a bounded set, and that the minimizer of the objective function satisfies certain conditions. The authors discuss potential extensions of their framework to more general GP regression problems, such as semi-supervised learning and hyperparameter learning, and acknowledge the importance of selecting effective sampling techniques for mini-batch points. Here is the combined summary. The paper presents a novel mini-batch method for Gaussian process regression, focusing on stability and generalization. The method approximates the Gaussian process posterior using mini-batches, ensuring stability and optimality by leveraging the properties of the GP. The proof of proposition 3.8 demonstrates the convergence of the mini-batch method. The authors draw inspiration from various works on stochastic optimization, weakly convex functions, and Gaussian processes, highlighting the importance of better models in stochastic optimization. The method is rooted in proximal duality, building upon the work of Moreau, 1965, and Nemirovsky et al., 2009. The authors develop an iterative algorithm that alternates between primal and dual updates, utilizing sparse Cholesky factorization. The primal update involves solving a stochastic optimization problem, approximating the objective function using a mini-batch of data points. The dual update involves gradient-based updates of the dual variables. The authors discuss connections between their method and other approaches, including sparse Gaussian processes, physics-informed neural networks, and numerical methods for solving nonlinear partial differential equations. The mini-batch method is demonstrated to be computationally efficient and scalable, suitable for large-scale datasets. A theoretical analysis establishes convergence guarantees and bounds on the error. The paper provides a review of the relevant literature, situating the author's approach within the broader context of machine learning, Gaussian processes, and numerical methods. The novel solution offered by the authors addresses the challenges of large-scale Gaussian process regression, ensuring stability and generalization.